Right, so today we have Lea Bottini tell us about non-invertible symmetries from Outer-Automorphism Gaugings. Take it away.
All right, okay, thanks a lot for inviting me to speak. And I wanted to discuss a bit this work, which is based on this paper in collaboration with Laksha Barwaj, my supervisor, Sakura Schaefer-Nameki, and Apurv Tiwari. So the starting point for this work is the idea that we should really think of symmetries as topological defects. And this idea really was a breakthrough in the understanding of symmetry because naturally it leads to a lot of generalizations. So, for example, we have higher form symmetries, which by now are quite well known. Then we have, for example, higher group symmetries. These are symmetries that mix higher form symmetries and more standard global symmetries. And in this talk, I will speak about this another generalization, which are non-invertible symmetries. Non-invertible symmetries are rather new in dimensions higher than 3, and there's been a lot of papers in the last year studying these symmetries and constructing approaches to obtain these non-invertibles. But the idea is that although they may seem weird, they are not exotic. So they appear in very familiar quantum field theories. So the plan of the talk is that I will review a bit this idea of topological defects and higher form symmetry, and then discuss non-invertible symmetries. And I will discuss how to obtain them by gauging outer-automorphism, zero-form symmetries. I will show this in 3-dimension quantum theories and in 4D quantum theories. And then if I have time, I will also discuss how to obtain them from another approach, which is based on some mixed anomalies. And finally conclude. Okay. So as I was saying, really the starting point is that this idea that symmetries are implemented by topological defects. This idea was there before, but it was really promoted strongly by the generalized global symmetry paper. And to understand where this comes from, we can consider a very standard example, which is a quantum field theory with a U1 global symmetry. And then Noether's theorem tells us that if we have this U1 global symmetry, we have an associated current, J mu, and this current is conserved. So it satisfies the mu J mu equal to 0 or d star f equal to 0 in form notation. And then using J mu, we can define an associated conserved charge. So this Q theta here, which is obtained by integrating J0 on a spatial slice. But in this talk, we consider only relativistic quantum field theories, and we work in Euclidean space-time. And then this conserved charge here can be promoted to an operator, d times d minus 1, which is obtained by integrating star j on a more general d minus 1 manifold, md minus 1. And the fact that d star j is equal to 0 translates, essentially using divergence theorem, translates into the fact that now d theta depends on the manifold only topologically. So this defines a set of topological operators in the theory. Okay, and this viewpoint is particularly useful if you have discrete symmetries, because for discrete symmetries, there is no current. And so we really take the existence of these topological defects as a definition of what we mean by there is this discrete symmetry. Okay, so what we find is that to global symmetry, G, standard symmetry, we can associate codimension 1 topological defects. And this is going to be...
One quick question. The sound is a bit weird. But maybe you can, since you're using your AirPods, I guess, maybe you could try using without.
I can try to not use them. Yeah.
Yeah.
It sounds like you're underwater. Try again.
It's also the Oxford Wi-Fi, I think. Your yellow.
Oxford Wi-Fi.
I thought it was just my Wi-Fi.
This
but
has
then-
nothing to do with Oxford Wi-Fi, I think.
So let's try now. Speak a bit.
It's good if I don't use
Oh, it
the...
sounds much better now.
Okay, cool.
Okay, cool, perfect. Thank you. Continue.
Okay, so this is gonna be my notation for the topological defects associated to the symmetry. This label here denotes the space-time dimension, and this label here, it's in this case a group label. So if we have a global symmetry G, we have one topological operator for each element in the group. Okay, and all the properties of these group G can be encoded in the topological defects. So for example, group law corresponds to fusion of these defects. You take two of them together, and then we produce a third defect, which now carries a label GG prime, and this is simply given by group multiplication in G. And as I was saying, this way of thinking is fruitful because it has immediately a lot of generalization. So one generalization is higher form symmetries. And these are characterized by the fact that you essentially don't consider codimension 1 topological defects, but you consider topological defects of higher codimension. So a codimension P, which is greater than 1. And correspondingly, the operators that are charged under these symmetries are not going to be any more local operators, but they are p-dimensional extended operators. So this is the standard picture. We have a p-dimensional operator, which is charged under this GP higher form symmetry. This naturally links with a D minus P minus 1 topological defect. And then this we can shrink, and we are going to obtain again our p-dimensional operator and a factor that measure the charge of the operator under the symmetry. Okay, maybe the simplest example of higher form symmetry in quantum field theory is free Maxwell theory in 4 dimensions. So in this theory, we have the gauge field A, from which we can define the field strength, and this satisfies the equation of motion. So this star F equal to 0, and the F equals 0, which is the Bianchi identity. But this means that in this theory, we have 2 closed currents, which are star F and F. And so by what I was saying, we can integrate them on an M2, and this allows us to define 2 topological defects, which I called one electric and one magnetic. And they are defined on surfaces, and surfaces in 4 dimensions generate a one-form symmetry. So we're going to get 2 U1 one-form symmetries. And correspondingly, we have charged operators that are lines. And for the electric one, these are Wilson lines, and magnetic one, Toff lines. So another well-known example of theory with gauge group G is pure Yang-Mills. Another example of theory with one-form symmetry is Yang-Mills, pure Yang-Mills with gauge group G. And this has a one-form symmetry, which is given by the center of the gauge group. And these symmetries can also be gauged similarly to standard symmetry. And if you gauge the center symmetry in this theory, you obtain a theory which has G mod the center gauge group. But the information about the original electric symmetry, the center, is not lost in the gauge theory because you obtain a dual magnetic symmetry in this theory, which is going to be a D-3 form symmetry. And this symmetry is valued in the Pontryagin dual of the center, which is simply the group of irreducible representation. So since the center is abelian, this is actually isomorphic to the group itself. And since I'm gonna use this a lot, maybe it's useful to revise why it's true that we have this general fact that if you have a P-form symmetry, G in your theory, and you gauge it, in the dual theory, you get a D-P-2 form symmetry, which is valued in the Pontryagin dual group. And the motivation is essentially the following. So the background field for a discrete P-form symmetry is simply a P+1 cocycle. So it lives in this cohomology group. And here I denote the partition function of the theory coupled to this background. But since I consider discrete symmetries, these are discrete symmetries, the partition function of the gauge theory is simply going to be a discrete sum over this AP+1, and it's going to be weighted by some factor here. And in this space factor, since A is a P+1 form, here we can put only a D minus P minus 1 form. But a D minus P minus 1 form on which now the partition function of the gauge theory depends is naturally the background for a D minus P minus 2 form symmetry. So in the dual theory, in the gauge theory, we obtain this dual symmetry G hat. Okay. And finally, another direction in which these symmetries can be generalized is non-invertible symmetry. And this time what we relax is the group structure. So you consider topological operators, but this time they do not fuse according to a group law, but they can have a more general fusion algebra. So you can have two topological operators, and they do not fuse into a single operator, but they fuse into a sum of other operators in your theory. And these kind of symmetries were studied and well known in 2 dimensions, where they form what is called a fusion category, and in part also in 3 dimensions, but they only, as I was saying, they only recently there have been like systematic approaches to constructing them in 4 dimensions and higher. And this is some of the proposal by various people to construct non-invertible symmetries. So one approach by these authors is based on mixed anomalies. So essentially, you have a theory with a global symmetry G and a global symmetry H, and these symmetries have a mixed anomaly. And if this mixed anomaly is of suitable type by gauging H, you can make G non-invertible. Another construction was by these people, and these are called duality defects. And the idea is that you need to find a theory which is self-dual under gauging a certain higher form symmetry G. And then you can gauge the symmetry only in half of space-time, and this is going to produce for you an interface which they show is a non-invertible defect. Then there are condensation defects, which again can be constructed by some gaugings starting from, and what I will talk about is how to obtain them by gauging, as I was saying, outer-automorphisms. And all of these approaches overlap in some examples, but all of them have a bit of different ranges of applicability. And some of the examples we derive here can actually be derived also using this mixed anomaly approach, but many of them don't. Okay. So our starting point will be a theory that only has invertible higher form symmetries. And we also assume that this theory has a zero form symmetry that acts on the other topological defects of higher codimension. And then the idea is that we gauge the zero form symmetry and the resulting theory as non-invertibles. So some examples are, for example, spin for n Yang-Mills, which has a Z2 charge conjugation outer-automorphism. If you gauge it, you go to pin plus, and this theory has non-invertibles. Another example is charge conjugation in U1 Maxwell theory. The resulting theory is O2, and also this has a continuous set of non-invertible symmetries. Or for example, spin 8, this actually has a S3, so a non-abelian outer-automorphism group. And also this theory has non-invertible once you gauge the S3. Okay, so to understand why gauging outer-automorphism leads to non-invertible symmetries, we can go back to the free Maxwell example in 4 dimensions. And recall that we found out that this theory has a U1 one-form symmetry. And for now, I will focus only on the electric one-form symmetry. And then this has associated topological defects D2 theta, 2 because they are defined on a surface. And this is the U1 label for the U1 one-form symmetry. And this theory has also a Z2 charge conjugation, zero-form symmetry. And this charge conjugation acts on the one-form symmetry defects. So it sends D2 theta to D2 minus theta. And in particularly, it leaves D2 pi invariant, and also D2 zero, which for me is the identity surface. And what we can do now is gauge charge conjugation and go to the gauge theory. And this example was also discussed in this paper here. And so the first thing to notice is that the identity surface and the pi surface are gauge invariant. So they simply survive the gauging. And D2 pi squares to the trivial surface. So it's a Z2 defect. And so it generates a Z2 one-form symmetry. And this was expected because O2 gauge theory has Z2 center. So indeed, we expect that there is a Z2 one-form symmetry left. But the other topological defects, these either D2 theta for theta different from pi, are not gauge invariant. And the idea is that instead of throwing them away, we can still keep them, but we have to consider now gauge invariant combination. So orbits under the action of charge conjugation. And then we define these new operators in the O2 gauge theory that are simply the direct sum of D2 theta and D2 minus theta in U1. And now if you consider the
Can I ask a question?
Yeah.
What do you mean by the direct sum there? Is it just means the usual sum in the operator sense?
Yeah. Here, yes.
Okay.
Thanks. And then if you compute their fusion, like S2 theta and S2 with a different angle, theta prime, we see that they don't fuse into a single defect, but into the sum of two other defects. So S2 theta plus theta prime and S2 theta minus theta prime. And so this is not a group-like fusion, and this gives us a non-invertible symmetry. So the discussion that I did so far is a bit naive because so far we considered only surfaces, but this is not the whole story. And in particular, since we are gauging a zero-form symmetry, we know that we get a dual symmetry in the gauge theory. In particular, yeah.
I'm sorry to interrupt. Could I ask another question about the last slide?
Yeah.
So when you find a fusion which closes on a sum of operators on the right-hand side, how do you know that that's necessary, that it's automatically non-invertible? In other words, how do you know that there's not a different basis of operators which kind of, I don't know what to call it, diagonalizes your, or maybe I should ask it as a question. Isn't that something that you need to check to know whether a given fusion algebra corresponds to a non-invertible one or not?
Well, but I guess another way of checking it is to see if you have elements for which you cannot define an inverse transformation.
There will always be elements like that because this is an operator algebra, so you're allowed to take sums of operators. So even just take a regular group fusion rule. The full set of topological operators isn't the group, but it's the what's it called? The group algebra. It's the sum of all linear combinations of group elements, and those in general are not invertible. But they're not. Yeah. It's a matter of there's a question of a choice of basis.
But the idea here is that we really take not the group algebra, just the symmetry. You have one operator for each group element, And for this act on some operator, and for each of these, you can always define an inverse operation.
Right.
Yeah.
So I'm just saying, when you're presented like an algebra, like the one you have at the bottom of that slide,
Yeah.
how do you know that you've chosen? I mean, might there not be a clever choice of basis? Probably, I'm sure it doesn't exist in this case, but I'm just saying in general, a choice of basis which makes it look, in which all the elements are invertible in that basis, and then it's.
Yeah.
In other words, the full algebra of operators is the, I don't know. In other words, how do you a priori know whether a given element is one of the, I could present for you a group, the group algebra of some familiar group, but I could choose some crazy basis, and it would be not at all obvious that this is a group, that this is the group algebra of a group.
Maybe we can discuss this afterwards.
Yeah.
Okay.
Okay. Okay, so far we discussed surfaces, but I was saying this is not the whole picture, because since we are gauging a zero form symmetry, in the gauged theory, what you have are line defects. And so these line defects are the ones that generate the dual symmetry, the D-2 dual symmetry. And what we would like to understand is like how all of these operators, line and surfaces of different dimension play with each other. And to understand it, it's convenient to consider first the 3D case, where one form symmetry is generated by lines. Because it's codimension 2, so in 3D it's lines, and then in the gauge theory we only have line operators. And this was studied also before in the context of 3D TQFTs in this paper here. So this is the setup. We have a 3D theory, which has a one form symmetry, and then we have a zero form symmetry, outer-automorphism. And we ask what are the topological defects in the gauged theory. So as I was saying, first of all, you get dual lines. So these are D1R, where R is an element of the Pontryagin duo. So I will call them also representation lines. And then, as I was discussing, you get invariant lines. So the operators from the original theory that survived the gauging are labeled by an orbit, and they are gauge invariant sums of operators in the previous theory. So they carry this orbit label. And finally, we can consider other lines that are sort of mixture of the above types. So you can have orbit lines that in addition are dressed with one of these D1R lines. And technically, what you can do is the following. You take an orbit O, and to an orbit you associate the stabilizer subgroup. So you take any element in the orbit, and you look at the elements of G that leaves it invariant. This is gonna give you a stabilizer subgroup. And then what you can do is dress this operator D1O with representations of the stabilizer to obtain these mixed objects D1O RO. Okay, so maybe this is a bit abstract. So I will discuss an example, which is spin plus for n in 3 dimension. Our starting point is a spin for n Purian-Mills in 3D. And this theory has the following symmetries. It has a one form symmetry, which is Z2 times Z2 coming from the center of spin for n. Here I call Z2S the subgroup that leaves the spinor representation invariant. This is the one that leaves the cospinor representation invariant. And then you also have a Z2V for the diagonal Z2 subgroup. And so correspondingly, we have 4 line defects, D1, the identity, and D1S, CV for the Z2 times Z2 one form symmetry. And they follow the Z2 times Z2 group law. So at this point, everything is invertible. So for example, D1S fuses with D1C to D1B, and each of them squares to the identity, etc. And this theory is also a zero-form outer-automorphism symmetry, a Z2, that acts by swapping the Z2S and the Z2C subgroup, leaving Z2V invariant. And what we can do now is gauge this Z2 charge conjugation and go to pin plus for an gauge theory. So this action of swapping the Z2S and Z2C induces an action on the one-form symmetry lines. So it's again gonna permute these two lines and leaving the invariant. And the picture is the following. You have a surface, which is the surface that implements charge conjugation. And if you cross it with a D1S line, it's gonna come out as a D1C line. So what are the lines that we get in pin plus for n? First of all, since we are gauging a Z2 zero-form symmetry, in 3D we get the dual one-form symmetry, which is again Z2, and it's, I call the generator of this symmetry D1 minus, where minus is the non-trivial Z2 element.
So what do you call charge conjugation?
It's this symmetry that permutes these two Z2s for me.
I see.
Is the one from the...
Is it justified to call it charge conjugation?
Well, it's yes, it swaps the spinor and conspinor representation.
They are not conjugate to each other. They are inequivalent representation. One is not charge conjugation of the other. Both of them are real representations for this symmetry. There are two cases to distinguish. There is 4 mod 8 and 0 mod 8. In both cases, it's a real representation. So I don't understand what is the notion of charge conjugation.
Yeah, then just take it as this Z2 outer-automorphism.
If you call it exchanging those two Z2s, that's good enough, but not charge conjugation.
It's, for me, it's the Z2 from the Dinkin diagram. It swaps these two representation and it swaps these two subgroup of the center. Okay, thanks. Okay, so these are the lines that generate the dual Z2 one-form symmetry. And then what we get as the lines S and C are permuted by this Z2 action, we get an invariant orbit D1SC, which is defined in this way. And since D1B is left invariant, we get, of course, D1B. And now we can compute the stabilizer subgroup of D1B. This is the full Z2 because Z2 doesn't act on it. So in addition to DV, we also have this stress version, D1V minus. We can think about it as D1V times this D1 minus line. And again, D1V is a Z2 line because as it remains invertible and in spin for n, D1V squared to the identity, it still squares to the identity, and it generates the center symmetry that we have in pin plus for n. So to recap, these are the 5 lines that we get in pin plus for n. The identity, the D1 minus line for the dual symmetry, this D1SC, and then we have V and V minus. Okay, and now what we want to do is try to determine the fusions of these lines. So the fusion of these 4 lines is quite easy to compute, and they have Z2 times Z2 fusion rules. So each one of them squares to the identity. And then you have, for example, that D1B times D1 minus is this line, D1B minus, and etc. So the non-trivial fusion that we want to compute is D1SC with itself. And what we can do to determine this fusion is go back to the pre-gauged theory, which is spin for n, and see what we get there. So this fusion in spin for n corresponds to this fusion here, where we write the operators as D1S plus D1C. And then the fusion, it's immediate to compute that it gives 2 times the identity line and 2 times the V line. This is pin for n. Now what we would like to understand is if in pin minus, for example, D1 identity or D1 minus appear, or D1V or D1V minus, what are the multiplicity of these lines? And what we do to determine this is look at these local operators here that live at the junction of the fusion of these lines here. So for example, let's consider the identity line, and to determine if the identity or D1 minus appear, we look at this junction space. And this is a 2-dimensional vector space, which is spanned by these operators here, because we have both that S and S going to the identity and C going to the identity. So this is a 2-dimensional vector space. And notice that the action of the Z2 symmetry swaps these 2 local operators that sit there at the junction of SS and identity and CC and the identity. So in particular, this vector space decomposes into the trivial and the non-trivial sign representation of Z2. And since there is an operator that transforms in the non-trivial representation, what we learn is that both the identity line and the D1 minus line will appear in the fusion. And now you can do exactly the same for D1V. And what you get is the following. So D1SC fuses with itself in the sum of all the other lines in the theory. And from the above, what you also get is that D1SC times D1V is again D1SC. And similarly, for example, D1SC times D1 minus is again D1SC. So also this justifies the stabilizer group prescription, in the sense that we see that if we fuse D1SC with D1 minus, we get again D1SC. So we cannot add an additional representation label on D1SC. And this is what we find in this pin plus for an example in 3D is the simplest non-group-like thing that you can have, in the sense that you have a set of invertible lines, D1A, where A is an abelian group, and these lines follow their fusion follows the multiplication rules given by the abelian group. And then you have just one non-invertible line. And if you fuse it with every D1A line, it still gives itself, but it fuses to itself into the sum of all the other lines in the theory. And what this is called a Tambara-Yamagami category. And in our case in particular, we find that it's the rep D8 Tambara-Yamagami. Okay, so after this 3D warm-up, let's finally move to 4 dimensions, which is what we discussed in our paper. And this is quite similar to 3D, but now the point is that you have defects that have various codimensions. So you have surfaces that generate the one-form symmetry, and you have lines that generate the dual symmetry. And what we try to do is to develop a consistent framework that combines all of these defects. So let's consider again pin plus for an Yamis in 4D. And exactly as in 3D, this has a one-form symmetry and a zero-form symmetry. The one-form symmetry is again a Z2 times Z2, and there is a Z2 zero-form symmetry. And the only difference is that now the one-form symmetry is implemented by surface operators. So we have, again, an S surface, a C surface, and a V surface. And what we do now is gauge, again, this Z2 and go to pin plus for n. So as before, the V surface is invariant, it stays there. S and C are permuted, so we construct a D2SC surface, which is the sum of those surfaces. And these have non-invertible fusion. D2SC times D2SC is the identity surface from the V plus the V surface. What about lines? So we can also consider topological lines, and in spin for n, there are no non-trivial two-form symmetries which are generated by lines. So we have no non-trivial topological line, but we can still think of trivial lines that live on each surfaces. So to each surface as C or V, we are going to have an associated line living on that surface, which is simply the trivial line living on that surface. And then what are the lines that we get after gauging? We get, first of all, the identity line and the minus line. Those are the lines that generate the dual symmetry, which in this case is a two-form symmetry, but in 4D it's still generated by lines. And then we get the D1SC line, which is the trivial line on the SC surface. And then we get, as before, D1V, and in stress version, D1V minus on the D2V surface.
May I ask a question about this this last slide?
Yeah.
So it's about in 4D in the non-invertible fusion.
Yeah.
On the previous slide. So
this one here.
Yeah, exactly. So these objects have a notion of dimension, right? Which is, I think, the size of the orbit in this case. And so this, I would say that the dimensions look like they don't add up in this formula because it's 2 times 2 is 1 plus 1. So how can this be a reasonable fusion?
Yeah. So what we argue is that these are local fusions that you compute in an open set of space-time where you, so on a completely trivial manifold, you fuse these two elements and you get the identity and the V surface. And indeed, it seems like the quantum dimension is not preserved. But then I'm going to discuss also global fusions. This is when you fuse two surfaces in a non-trivial manifold. So in particular, you have non-trivial one cycles where you can rot lines. And these lines are going to appear here, what I called before the D1 identity and the D1 minus line. And in the same here, you're going to get in a fusion involves also the D1V and the D1V minus line. So if you take also lines to account in the fusion, then you preserve the quantum dimension.
But I think these should probably be included. These are condensation defects, right? So I think they have to be included as simple objects in the category. And so
yeah, but so far,
I think they should still appear.
Anything in a categorical language. But yeah,
they should still appear in the fusion rules as a simple object. So this whole right-hand side should probably
I agree. Indeed,
should be multiplied by a condensation defect.
Yeah, indeed, we think that global fusions are the proper fusions in the category. Here, what I'm discussing is what we call local fusions that are simply computed in an open set without any other defect present. In that case, you don't see the lines, so you simply get these. But yeah, I agree that in the category structure, the simple objects should include the condensation of lines. And in that case, indeed, we preserve the quantum dimension.
Yeah.
Yeah, thanks.
You will mention this, no, later.
The global fusions?
Yes.
Yeah. Here I'm not framing it in a category language, but yeah, if you do so, then you'd have to consider condensation on top of this fusion. So as I was saying, the fusion of lines is the same as in 3 dimension. So we get again that D1SC times D1SC is the sum of the other lines. But now we see that on the right-hand side, we see lines that live on different surfaces. So the interpretation is a bit different. What does it mean that 2 lines on the SC surface can fuse 2 lines living on different surfaces? And let's consider, for example, D1 minus. The fact that D1SC times D1SC can fuse into D1 minus, we interpret it as saying that D1 minus line can end on the D2SC surface. So there is a local operator here with non-trivial Z2 charge on which the D1 minus line can end. And remember that D1SC is the trivial line on the D2SC surface. So you can either draw it or not draw it, but this gives indeed rise to a fusion. D1SC is D1 minus. Okay, and so far what I considered are, as I was saying, local fusions. So these are computed in an open set of space-time without any other defect present. Now, what we also want to understand is what happens if you take into account also the global aspects of the manifold where you're computing the fusions. And what we discuss in the paper, in a nutshell, is that global fusion of a defect dp1 and a defect dp2 is described in addition by performing a gauging of the symmetries that are localized along dp1 times dp2. And the specific gauging that we need to do is specified by the local fusions of higher codimension defects. So for example, if we consider surfaces, then we have that the global fusion of these two surfaces and the gauging that we need to do on top is specified by local fusions of lines. So let's consider again pin plus 4n in 4D, which has this local non-invertible fusion. D2SC times D2SC is identity plus V. And now we want to compute this fusion, but a non-trivial compact sigma 2. So what we need to do is find out what are the symmetries that are localized along the identity surface and the V surface. And since we have D1 minus, which is a bulk line, but we can still think of it associated to an identity surface, and D1V minus, this means that there are two, and both of these lines squared to the trivial line. This means that there are two Z2 zero form symmetries, one localized along the identity surface and one localized along the V surface. And these are zero form symmetries from the point of view of the surface because they are generated by line, but they are two form symmetries from the bulk point of view because in 4D lines generates a two form symmetry. So we have these two Z2 zero form symmetry on the surfaces. And what this does is that the fusion on this non-trivial sigma 2 is realized by on top of the identity and the V surface by gauging these Z2 zero form symmetries that are localized there. So this quotient here should mean that we are really gauging this Z2 zero form symmetry. And let's consider this identity surface where we are gauging the D1 minus line. So here what we are doing is that we are taking a two form symmetry line in 4D, and we are gauging it, but not on the whole space-time. We are gauging it only on a surface. And these are exactly called condensation defects. They've been discussed recently in these papers, and they have appeared a lot in this non-invertible story. And they are indeed obtained by taking higher form symmetry and gauging it, but not on the whole space-time, gauging it on a higher codimensional manifold, which is what we are doing with the D1 minus and gauging it on a surface. And global fusions are interesting because they can also be checked with the mixed anomaly approach that I was mentioning. And the idea is the following. It was discussed in this paper. And it's to consider a d-dimensional quantum field theory that has global symmetry G, and this G is a product of higher form symmetries. Or I can include also zero form symmetry. And now suppose that this theory has a mixed anomaly, which is a particular type. So take a G P form symmetry subgroup of the global symmetry and assume that the mixed anomaly is linear in this background for the P form symmetry. So the anomaly is something like that. It's AP plus 1, and then here you have a function of the other backgrounds. And here ND+1 is a D+1 dimensional manifold whose boundary is MP that we use to define the anomaly. And then the proposal by these authors, well, the standard idea is the following, that because of this mixed anomaly, the topological defect associated to this P-form symmetry, which is a D minus P minus 1 defect, is anomalous under background transformation of the other fields. So in particular, if we now gauge all the symmetries except for GP, this becomes ill-defined. And this is the standard statement that if you have a mixed anomaly between global symmetries, you gauge part of the symmetries in the mixed anomaly and you completely break the other symmetries. But the proposal by these authors is that you can actually save this symmetry here. You can save this topological defect D minus P minus 1 if you stack it with a TQFT that lives only on the defect and which has precisely the anomalic psi. So instead of breaking the symmetry, you can still have it if you put this TQFT that absorbs the anomaly. But the price that you pay is that now this composite object, which is the D minus P minus 1 defect times the TQFT, is non-invertible. So it doesn't have simple fusions. And our idea is that a lot of mixed anomalies can actually be produced by starting with theories that have non-anomalous higher group symmetry, as was discussed in this paper by Tachikawa. And so the idea is this: we start from a theory with a higher group symmetry, we get a mixed anomaly, and then we are in the setup to run this approach. Okay. So let's consider again our favorite example, spin for n, which again, this has a Z2 times Z2 one-form symmetry and the Z2 zero-form symmetry. And they form what is called a two-group, which in terms of the backgrounds for these symmetries reads delta B2 equal A1 C2. So here B2 is the background for this Z2B subgroup, C2 is the background for this Z2 subgroup, and then this is the background for the zero-form symmetry. So this is a one form and these are two forms. And now if you gauge B2 here, you go to SO for n theory, and this SO for n theory has a mixed anomaly, which is A1, C2, and B2 prime. And here we are gauging a one-form symmetry, this Z2B. In fourth dimension, you get a dual one-form symmetry, a Z2B prime, and I call B2 prime the background for this dual symmetry. So this is the mixed anomaly, but you see that it's a mixed anomaly and it's linear in the background for each of these fields. So we are in the right setup to run the construction that I described earlier. So in particular, what I want to do now is to gauge A1 and B2 prime and make the defect for C2 non-invertible. And so what are essentially doing by gauging A1 and B2 prime? By gauging B2 prime, remember that B2 prime is the background for the dual symmetry. So we are essentially gauging the dual symmetry, which means that from SO for n, we are going back to spin for n. And then I'm gauging A1. So this is like gauging the Z2 in spin for n, and the net effect of this series of gaugings is just to gauge pin plus for n. And then what I defined is this defect n. This is D2, where D2 is the defect for this Z2C symmetry associated with this background. And then what I put here is simply a TQFT that lives on the defect. And this TQFT is cooked up such as this, its anomaly precisely cancels this one. So this total N2, which is the D2 with the TQFT, is non-anomalous. And so it remains after gauging. Okay, and what we find is that the fusions are the following. So essentially this NM2 fuses with itself to give 1 plus the identity surface plus this T surface, and then a sum of lines. Here, TM2 is the surface defect for the C2B symmetry. And these here are lines, and they are the lines that surfaces. And this is exactly condensation, because we are taking the lines for the dual two-form symmetry, and we are summing over them, but on each one of them two, not of the whole space-time. So this is precisely gauging the two-form symmetry only on a surface. And then we find that N with T fuses again to N, and N with L gives again N. So if we compare to the fusion that we found, the identity surface and the V surface and the gauging, the additional gauging, this is exactly the same result. If we identify our non-invertible D2SC surface with this N surface, then the D2V is this T of M2 that indeed also generates a Z2. And then we identify the D1 minus line with this L line. Okay. And so spin for N was particularly interesting for us because it allows to check very different construction of non-invertible symmetries and see that they indeed match. But there are examples that so far we can do only in certain approaches. So for example, we can do gauging of finite non-abelian symmetries, for example, S3 in spin 8, that cannot be done with the mixed anomaly approach, or also have continuous non-invertible symmetries, like the ones that you get in O2 gauge theory. And for example, these authors in this paper describe even more complicated non-abelian gaugings. And there are also a lot of examples that I didn't discuss. So for example, spin for N times spin for N gauge theory. So finally a Quiver with matter in the bivector representation as a D8 outer-automorphism. So you can also do a D8 gauging there. And then there are examples in 5D supersymmetric gauge theories or also 6D CFTs. So to conclude, we found example of these new non-invertible symmetries, and then because they appear in very familiar gauge theory examples. So this is very nice, and it's telling us that there are stories actually more complicated than we thought. But what I think would be really interesting at this point is to find really some new physical implications of non-invertible. So now that we know that these symmetries are there, can we derive new constraints on the dynamics of these theories that we all know? And there are some papers and there are some ideas that you can indeed use these symmetries to do anomaly matching and find constraints, but this is really a direction that should be explored more now that we have access to all these new symmetries. Another thing are learning how to gauge higher form symmetries in this approach, because so far what we've done was to gauge zero form symmetries, but these theories have also higher form symmetries, and using different approaches you can also gauge them. So what we are trying to do now, this is a work in progress, and we are doing gauging of higher form symmetries using this orbits approach, etc. And finally, one point is that we describe in the paper how we expect that the mathematical structure that in the end should be describing all of these defects, it's what it's called a higher fusion category. And this is a topic that in mathematics is not very well developed yet. So it would also be nice to have develop more the mathematical framework in which we believe in the end all these things should be put. So that's it. Thanks a lot.
All right, let's thank Lea. And questions? Okay, there's a question in the chat. Craig?
Yes. Thank you for this nice talk. I wanted to ask about the pin plus example. So
yeah,
worked out the fusion algebra by looking at the vertex in the spin 4n theory.
Yeah.
So if I understand correctly, you have a choice of decorating the vertex, like the intersection point, with a choice of topological defect for the one form symmetry.
Let's go back. Here.
Yeah. So I'm kind of asking, which choice did you make there? And does it change the answer if you decorate it with different choices of, does it change the fusion algebra if you decorate it with different choices of codimension 2 defect?
Yeah, so I wouldn't say it's really a choice. You simply look at this vector space that you have there, and this is given for you by the fusions in spin 4n. And then you find that this is a two-dimensional vector space, which is spanned by these two operators. And these operators are acted upon by charge conjugation. Then you can sort of find an even combination, which is the sum, and an odd combination. And then you have both this even combination and odd combination sitting here at the junction. So this is telling you that both D1 identity and minus will appear there. If you don't have, suppose for example that this is a one-dimensional vector space. So it will never give you the D1, non-trivial representation under C2. So this is automatically telling you that only the identity line will be there in pin plus. The idea is that you look at this junction space, you decompose it into representation of the symmetry you're gauging, and all the representation that you find there then are going to give lines in the gauge the theory. If you want, you can think of it maybe this way, like.
So just to make sure I do understand. Or to make myself be more clear. So I was referring sort of obliquely to these papers from a couple of weeks ago by like Cordova and Komargodski and a host of collaborators who I shouldn't forget, where they said that to actually define the theory in the context of having both a 0 form and a 1 form symmetry, you're forced to pick a choice of codimension 2 defect at the intersection point of codimension 1 defects. And their argument is that these are always different, or maybe not always, but that these are generally speaking different theories.
So I'm not familiar with what they discuss in that paper, but here the statement is simply that maybe we can think of it this way, that you have, let's say, the fusion of these lines. This is in spin.
Yes.
And you find here that there is a local operator that transforms in a representation R. Then we go to the gauge theory, and you get again this configuration, but now this operator R is not gauge invariant anymore. So you need to attach a Wilson line in a representation R to make it gauge invariant.
I see.
And now this composite object which is a line D1O, and we conspire to form D1O RO. Simply the statement of why having an operator charged will tell you that in the end you have this operator here. That's this answer.
I see. Okay, I think I
So,
understand.
I mean, I think what you're asking is about co-cycles and things like that, right? And here there's no choice made, so it's like a trivial declaration.
But it could be non-trivial if you.
I mean, you can generalize this, but I think this is sort of here, we don't consider these additional structures.
Okay. I guess my question was, if it is there, might it change the algebra on the next page?
Yeah, I think it would.
Okay, cool. Thank you.
More questions? All right, if there are no more questions.
I actually do have one more question. I was just going to give someone else a chance. So in the other approach to the pin plus, where you look at the mixed anomaly,
Yeah.
you picked a choice of TQFT that cancels the anomaly.
Yeah.
And then you said, if we pick this and look at the, treat this theory as the defect, then we see the same non-invertible structure.
Yeah.
Is there a uniqueness argument of something for this choice, or could you have picked something else, which?
For the choice of TQFT?
Yeah, for the choice of this N2.
Yeah. So in the paper, in the original paper where this approach was discussed, they have a particular mixed anomaly, which is of the form like A1 Pontryagin in B2.
Mm-hmm.
So an anomaly 1. And the TQFT that you need to attach in this case is a TQFT which has this anomaly. And for this specific case, there exists a notion of minimal TQFT with that anomaly. It says that you pick always the minimal choice, because it can be shown that there is a TQFT, all the other TQFT can be written as the minimal one plus a decoupled TQFT that doesn't talk to the one from symmetry. For this case, the anomaly is different. So in our sense, our choice is minimal. So it's the simplest TQFT you can think with that anomaly, but I don't think it's a unique choice. And in general, you may find decoupled sectors or things like that if you pick a more complicated TQFT.
Okay, cool. Thanks. Yeah, thanks for the very nice talk.
Yeah, thanks.
More questions? Okay, so if there are no urgent questions, then let's thank Lea again. I'll stop the recording.